Okay, this is David Zierler, Director of the Caltech Heritage Project. It's Thursday, February 17th, 2022. It is great to be back with Professor Nicholas Scoville. Nick, it's good to be with you again.
Yeah, and thank you for the previous interview. It was great.
I want to go back to some of the additional research from your time at Owens Valley. What were you saying there about your main line of work?
My main line was the ultraluminous infrared galaxies were discovered by the IRAS satellite, which Gary Neugebauer, professor in physics, was PI on. And they discovered these objects which had huge inferred luminosities in the infrared, but only maybe 1% as much luminosity coming out in the optical. So they were clearly very interesting dust enshrouded objects. There were even people like Frank Lowe, who's an infrared astronomer in Arizona, who suggested that maybe there was some new object called IR-tron, and people kind of didn't take it very seriously. But in any case, they were highly obscured, and the thing is, the resolution which they'd had previously on these objects was only of the order of an arc minute. So although there were optical images which were higher resolution, obviously down to 1 or 2 arc seconds, but the thing that I wanted to pursue was where the gas and dust were in the galaxies relative to what you see in the optical. And we had the ideal instrument to do that with, which was the Owens Valley millimeter array, which originally consisted of 3 telescopes, 3 10-meter latent dishes. But then while I was director, we actually got funding for both from the NSF and from the Norris Foundation for an additional 3 telescopes. And so we actually had a 6 telescope array, which gives you, like 15 baselines and, fairly quick imaging compared to what we had before.
That's a real abundance of riches right there.
Yeah. Now, of course, the lead millimeter array is the Alma array in Chile, which has actually 64 telescopes, and they sort of guarantee 45 operating at the same time. So that's roughly 1,500 baselines observed. So that's order of magnitude, more better for imaging and sensitivity. In any case, the project I set out to do was, and this was actually before the Sanders and Sofer and myself included paper linking ULERGs to quasars. Mm-hmm. What I set out to do was to locate where the dust and gas were. We already knew that there was a huge amount based upon single dish observations of the flux, say in the CO line. But what I set out to do was to get down from 1 arc minute, typically resolution, down to sub arc second, meaning of the order of 0.1 arc second imaging. And what we discovered actually in the case of the most obvious nearby such ULERG called ARC-220, what we discovered was that, in fact, you could see both nuclei in the galaxy. Both had gas and dust surrounding the nuclei. And then when we looked at the velocity field, this was a postdoc working with me. When we looked at the velocity field, we found that the 2 disks in the gas disk in the nuclei of the galaxies hadn't fully merged, but they're about 300 parsecs apart. The kinematics indicated that they were counter-rotating, and thus it's easy to understand that these galaxies could merge very quickly because the orbital angular momentum, internal angular momentum within the galaxy gets canceled out from one galaxy to another as they mix their gas and dust and star system. In the case of the stars, the individual star kinematics don't change that much because the stars have no way of getting rid of their kinetic energy of motion except through very slow processes. But the gas, once you collide two gas clouds, as I think I said earlier in this interview, you dissipate the kinetic energy of relative motion of the gas clouds. And you also, can cancel out angular momentum as you would have in a counter-rotating system with colliding galaxies. So then ultimately I followed that up with high resolution observations of the Alma array once it was operational. And
what year was that, Nick? When did Alma go online?
Alma came into operation roughly around 2010. And one of the first proposals I submitted, which I think was done in 2011 or so, was to do ARC 220 at high resolution, roughly 0.2 arc seconds, 5 times better than what I've been able to get with the Owens Valley array. And there I actually found that not only was the gas centered on the two nuclei, but it was incredibly concentrated. And so,
which tells you, what does that tell you? Its concentration.
Well, the concentration tells you what the gas density is, and also what the opacity to any visible radiation originated from the two nuclei. So, just to give some numbers, the most luminous infrared nuclei of ARC 220, that one had a dust concentration around the nucleus, which was about 3 times 10 to the 3 billion solar masses, which is equivalent to of gas, which is equivalent to all the gas in the Milky Way squeezed down to 30 parsecs diameter. It was really quite incredible. In the Milky Way, most of that gas is out at 5 to 10 kiloparsecs from the sun inward. The fact that you've concentrated the gas so much means that, one, obviously, there'll be a high opacity and you can't really directly see the nucleus, but the rate of star formation will be that much higher because gravitational collapse is much easier to initiate when you start with gas at density 1 million per cubic centimeter, 1 million molecules per cubic centimeter, as opposed to a standard giant molecular clouds in our galaxy, which are maybe 300 molecules per cubic centimeter. So, that was extremely exciting work. And it was a pleasure to take part in. And the later investigations, actually, I collaborated with Dave Sanders throughout it. But the initial observations were actually done before the paper linking quasars with ultraluminous infrared colliding galaxies.
Nick, I'm curious, once Alma came online, to what extent did it render Owens Valley observational capacities obsolete, or were they more complementary at that point?
Well, they could have been a little bit more complementary, but Owens Valley relied upon NSF funding for a major part of its and the so-called Karma array for most of its financial operating money. And so, obviously once the NSF decided that, they'd already put something like $150, $200 million into the Alma array, they basically backed off supporting the university arrays. And so, it's kind of a foregone conclusion that they wouldn't be supporting the university arrays in the future. On the other hand, there were some projects which were sort of large-scale mapping of nearby molecular clouds, which were very successfully done with the Karma array. And, those results have been published. So.
Nick, I'm curious, what about the distinctions between Northern Hemisphere versus Southern Hemisphere observation? What are some of the challenges and opportunities there?
Well, one challenge is that there are unique telescopes in the two hemispheres. And I think I mentioned last time in our interview that that's particularly the case in radio wavelengths, where you have the so-called EVLA, which is in New Mexico, which does centimeter wave radio observations. And then in the southern hemisphere, you have Alma, which does higher frequency observations. And basically the latitudes of those two observatories are plus and minus 20, 25 degrees from the equator. So, it becomes a little bit difficult to do something which is in the north by more than 20 degrees from Alma. And likewise, something is more south than 20 degrees can't be done well at the VLA. So, on the other hand, it's very complementary data from those two telescopes. So, that's an example of, where one of the motivations in Cosmos, and we can get into discussing Cosmos at this point, was to have a field in the sky where you could observe with telescopes in both hemispheres. That's worked out incredibly successfully, because not only do you have these two radio telescope arrays, the EVLA and Alma, but then there are large telescopes in the southern hemisphere at the ESO Observatory, which I think has 4 8-meter telescopes, in addition to other smaller telescopes. And then, of course, in the northern hemisphere, there are the twin 10-meter telescopes of the Keck Observatory. And, the Cosmos survey, we put the field on the equator. It's only 2 degrees off the celestial equator. And that has enabled us to collect data from not only unique telescopes, but also large telescopes in both hemispheres, from which there's a limited amount of time.
What is celestial equator? What's the difference between that and a terrestrial equator?
It's the line in the sky directly above the Earth's equator. And so you obviously probably know that the Earth's rotation axis is tilted by 23.5 degrees to the axis of the ecliptic around the path of the sun and the planets around the path of the Earth and the planets around the sun, being the ecliptic. Well, that was garbled. But anyway, you can excise and
no. It was great. It was great.
The life. But in any case, I, being particularly interested in the millimeter and submillimeter imaging of objects, insisted that we should have a field that should be observable by Alma, because obviously that was the big new future instrument. But then also we've accumulated very good data from the EVLA, but a lot of our optical and near-infrared imaging has been obtained at both ESO and at Keck and other telescopes in Hawaii. So, the strategy has worked out extremely well. And I should tell you how Cosmos actually got started.
Yeah, just to orient us chronologically, when did those earliest discussions start that ultimately led to Cosmos?
Okay, so the first planning was in 2002, and it was initiated by a kind of fluke on the part of people complaining. The Hubble telescope has a call for proposals once a year, and in the previous call, it turned out that the large projects which were selected to have Hubble observing time, that is the Goods survey, and I think there were 1 or 2 other projects which I don't remember what they were, probably in a different field than external galaxies. The projects which were selected were all PI'd or had heavy collaboration from people at Space Telescope Institute. So there was a complaint on the part of astronomers at the universities and other facilities that somehow there was a bias in the selection or the capability to write proposals. And I felt a little bit embarrassed by people complaining. There were people at Caltech who complained, not myself. But in any case, the director of Space Telescope Institute at that point was Steve Beckwith, who used to be a graduate student at Caltech and then went on and became a professor at Cornell and then ultimately director at Space Telescope Institute. He decided that they would have a workshop to decide what big projects to do in the next HST proposal cycle. And these big projects are typically, 100 orbits or so of HST time, as opposed to, typical small projects, which might be a few orbits up to 10 or 20. So, it's very, what big projects are done is extremely important. And he asked me to chair the sub-panel in that workshop, which dealt with cosmic evolution and cosmology. And there were maybe 30 people invited to the workshop who were external galaxy people who did surveys at high redshift and whatnot. But in any case, I was picked to lead it, maybe because Steve thought that I was impartial or maybe had a good physical sense about what was important to do. I'm not quite sure. But in any case, when I looked at what I hadn't really done observations in that area, so it was a little peculiar that I was chosen to lead this workshop. But it's good also to have somebody who doesn't have an agenda, leading the discussion. When I looked at what had been done and compared with the predictions of cosmological simulations, it was glaringly obvious to me that the previous fields, such as the Hubble Deep Field, and then subsequently there was one called the Hubble Ultra Deep Field in the Southern Hemisphere, that these fields of the order of a few arc minutes in size were way too small to map out the large-scale structure at high redshift in galaxies. And at this point in 2002 to 2003, it was believed that a lot of galaxy evolution is actually determined by their so-called environment. That is, how many galaxies are nearby? Is the galaxy located at the core of a large-scale structure or in a filament or in the intervening space between filaments? And if you looked at the size of these previous fields, the large-scale structure would be, the scale of large-scale structure might be 50 megaparsecs or so. And then the scale of these fields was sort of like this. So we put a figure ultimately in the Cosmos proposal, which became the Cosmos survey. And I think that was what really got the proposal selected.
What were the conceptions of who would be collaborators at the international level of Cosmos?
Well, at that workshop, I said, anybody who wants to be a collaborator on this proposal, which I will write, I would welcome them to join in. And that included a lot of Europeans who had attended the workshop, such as Alvio Renzini and Olivier Lefebvre. And so, we had tremendous international representation on the project. But backing up just a second, there were other people on that workshop panel who, wanted to write their own proposal. And one of them was Professor Sandy Faber from UC Santa Cruz. And she was kind of incensed that here was somebody who had done mostly radio and infrared astronomy was, submitting a proposal for a large amount of Hubble time. So she submitted a competing proposal, and ultimately the TAC selected our proposal. Hers was to do a strip in the northern hemisphere, which she'd been focusing on in her previous studies. But it was a narrow strip and wouldn't really get around the issue of how do you map the large scale structure if you're only looking at a small area of the large scale structure. And so, we actually got selected, and she unbecomingly actually complained to the observatory director, who still was Steve Beckwith, and he rejected her claim. But, it was kind of unpleasant. You're not supposed to go outside the proposal review process. Ultimately, she did get time a year or two later to do some of the work that she wanted to do. So I think in the end, she ended up happy, but, she didn't like being so-called superseded. The previous largest proposal, which I think was the Good Survey project, which had been done, as I said, in a previous cycle, that was probably 150 orbits or so. So it was several pointings, but then in several bands going deep with multiple orbit exposures on each of the pointings. That had involved roughly 150 orbits, and the proposal which I submitted, which became Cosmos, there we proposed 600 orbits. So when it actually got selected, it was quite amazing. It was, 3 or 4 times as large as any previous proposal done at HST. So roughly there's 300 orbits per year. And so it's like 20% of the time in a year or two.
Nick, what were some of the main research questions that prompted the creation of Cosmos? What was not possible without this new collaboration?
The main one, as I said, was the correlation between cosmic large-scale structure and the properties of galaxies. And you might expect that in an area of the large-scale structure where in the core of the large-scale structure, where the density of galaxies is very high, that their galaxies will evolve more rapidly. And in addition, that may be the place where collisions of galaxies leads to the morphological transformation from spiral galaxies with disks and lots of gas to elliptical galaxies, in which basically are a spherical ball of stars with no remaining gas and aging stellar population because they no longer have star forming gas. So that you expect that kind of correlation, but it hadn't really been observed except in a few local clusters where you would see ellipticals in high density regions, but not at cosmic distances, redshift 1, 2, 3, at the peak of star formation. So that was the prime objective. The first exciting project, which was really done, was done early, was that of detecting gravitational lensing by an amplification by foreground galaxies of distant galaxies in at high redshift. And so this was a project which was led by Jason Rhodes and Richard Massey, and Richard Ellis was involved in it. And I was, of course, a collaborator on it, but I didn't really do a lot on that project. But that actually became a cover article for Nature at the time, because there actually was a correlation in the mass distribution deduced by the lensing of background, or an amplification of background galaxies, and where the galaxy density was high in the foreground. So that worked out beautifully. If you actually look at their dark matter mass distribution, it's, kind of deficient in the sense that, the dark matter sort of extends over a large range of redshifts. But that's because of the limited sensitivity of the weak lensing observations. It's not due to any deficiency that you wouldn't expect. Then, one of the projects which I focused on was the mapping out of the large-scale structure. Now, in the Cosmos survey field, we were doing 2 square degrees, so that's roughly 1.5 by 1.5 degrees on the sky, and it's equivalent to something like the area of 9 full moons, stacked next to each other. So it's a huge area on the sky, and let's see, what was it? Where was I going? In order to define structure and where a galaxy is, you of course need the redshift of the galaxy, which infers, where that galaxy lies in the overall cosmic expansion, which is, producing the redshift. And so, at redshift 2, all the light from the galaxy is shifted by a factor of 3 to longer wavelengths by that cosmological expansion, because the galaxies and us are separating at a significant fraction of the speed of light. And so there's a Doppler shift of the radiation from those galaxies that comes to us. And in the cosmos field, which, as I said, was 2 square degrees across, the imaging that we got with Hubble indicated a sample of roughly 900,000 galaxies. And there's no way that you contemplate getting spectroscopic redshifts, where you typically do 1 at a time or 10 or 20 galaxies at a time, to cover the whole field and thereby map out the large-scale structure. And if you don't have redshifts, what you see is all these galaxies on the sky, 900,000 of them, but you can't tell whether one galaxy is associated with another without knowing the redshift and knowing that they're similar distances. So one of the things which and I think I was one of the ones who initiated this, realized at the beginning that we would need to use a technique which are called photometric redshifts, where you take imaging of the galaxies, which in the images at each wavelength, you can cover, 1/5 of the field of cosmos. Then the Subaru telescope actually built an imager which was actually matched to the cosmos field of view. And so we could actually use that camera, it's now called Hyper Supreme Cam, on the Subaru telescope, to do multi-band imaging, deep, many exposures in the same pointing, but then multi-band imaging of the cosmos field, which then gave us, in the red filter, you see the light which is coming to us at red wavelengths, blue filter, blue wavelengths, and so on, all the way down to the infrared, roughly 1 micron. And then there was another survey which was started about 10 years after Cosmos, called the Ultra Vista survey, which was operating in the near infrared, that is out to 2 microns wavelength, or 4 times the visible wavelength. That survey actually made a near infrared map of the cosmos field, which is probably the deepest near infrared map of any field in the sky. So then what you do is you take each galaxy and each band image and measure the flux seen in that band from that galaxy, and then try to match that to the predicted flux of different types of galaxies, like spiral galaxies, elliptical galaxies, small regular galaxies. Match it to the local galaxy so-called spectral energy distribution, And, if you get a match, you can then determine the so-called photometric redshift of the galaxy, which, you know, initially at the time when we started Cosmos, those photometric redshifts were only of accuracy sort of zero point 0.1 in redshift. So they wouldn't allow you to really map out very well the large scale structure. But then as a result of this high quality photometry, and now in Cosmos we have 41 bands from ultraviolet down to near infrared. With that number of bands, you basically get spectra which have resolution 40 or 50 to 1. And we now have 1% or better accuracy on roughly 600,000 of these galaxies. And the limiting, the remaining galaxies are a little bit too faint to get quite as high accuracy. So, that worked out beautifully. And I was able to use those photometric redshifts. And this was first in a paper in 2009 to map out the large-scale structure in the whole Cosmos survey field. And there was something like 100 structures which we could see at different redshifts, which would extend sort of halfway across the area of the field. And then there was another paper I wrote in 2013, but then there was a student of the Professor Bahram Mobasher at Riverside who also, repeated what I did and basically found, the same structure. But, I let him take over that area of investigation. And, then when I looked at the correlation between the galaxy properties and the location of large-scale structure, we saw kind of what you actually expect. That is, in the dense regions, you would see more rapid. The other thing you get is you can, once you've done maps at different redshift, is you can see the overall cosmic evolution of galaxies and how it is correlated with the development of the large-scale structure. So we've found that in the dense areas of large-scale structure, at low redshifts, the galaxies were very largely elliptical type galaxies with red stellar populations, meaning older stars. But then when you went out to redshift 2 or 3 at the peak of cosmic star formation, there was very little segregation in the galaxy types. So the implication is that it takes a while for the environmental influences to play a role in the galaxy transformations, say from spiral to elliptical galaxies. And the difference occurs around, when you can start to see it very clearly is around redshift 1.2 or so. And it turns out that, the more recent study, which I think I described using Alma to measure the gas content of the galaxies, at redshift 1.2 and higher redshifts, meaning earlier in time, that's the area where gas dominates the stars. But then as you go to lower redshifts and later cosmic times, closer to the present epoch, the gas content is smaller than the stellar mass content of the galaxies. So that sort of goes along with the picture I was painting of the galaxy transformations, which is that, once you've started to use up most of the gas content in the galaxies, you no longer form young stars. And obviously, a galaxy can no longer form a spiral galaxy disk, which is largely young stars, and the gas which forms those existing young stars. So, the Milky Way has escaped this transformation simply because it's in a low density cluster along with the large Magellanic clouds and the M31 and M33. But it's in a low density environment. There hasn't yet been a collision between, say M31 and the Milky Way, but that's projected to happen in the future.
Nick, what were some of the key funding sources that made Cosmos possible?
Well, is there a difference between NASA and NSF? in the case of Hubble telescope projects, and with JWST also, James Webb Space Telescope, if you get observing time, you also get funding for postdocs or whatever you need. And there's a so-called Hubble constant, which nobody knows what the JWST constant is, but that for an orbit or so many hours of observing time, you get maybe $5,000, $10,000 of financial support per hour, and you can basically predict what each PI will get. And in the case of Cosmos, we had 600 orbits, as I said, were granted to us. We ended up with $2 million of funding which came from NASA ultimately, but it was funneled through the Space Telescope Science Institute. And, that gives you a fair amount of discretion and power. And I distributed it around, but my attitude about funding is, I've seen scientists get in trouble with their funding, and primarily because, they overextended, their hiring of postdocs, supporting people on travel. So I didn't, say take all the U.S. COIs and equally divide the funding. I decided, where some of the work would really be done, and divided it accordingly, and then kept a fair amount here in order to help people out when they ran out of funding.
Nick, administratively, how much time did Cosmos take out of your schedule?
For administering Cosmos project, very little time. But, my research for the period of 10, 15 years was largely focused on the Cosmos field. And, this Alma project I've been doing, it doesn't involve Hubble observations, additional Hubble observations, but it is in the Cosmos field. And so it wouldn't have been done without having the Cosmos survey. So, when you have 800,000 galaxies with known positions, redshifts, meaning cosmic time, then you can do a lot with that sample of galaxies. Whereas most surveys, like these ultra deep fields, the Hubble ultra deep field and the Hubble deep field, they may have 500, 1,000 galaxies in the field. So that gives you limited statistics to do much with, correlations between galaxy properties and cosmic time or cosmic environment. So, once you've accumulated this vast, as I said, 41 bands of photometry on, every galaxy in the field, that gives you tremendous ability to go to other telescopes and make use of them to survey, say, all the X-ray objects in the field, which might be active galactic nuclei or supermassive black holes. And, that's been done by a lot of the Cosmos COIs. But one way I ran the project, and this resulted in my not getting stressed out by it, because the initial proposal had 38 COIs, and typically, throughout the last 20 years of Cosmos, we've had 100 people actively participating in the project and coming to team meetings, which are once a year. So my attitude has been, and we established this as a rule, a lot of projects like the Sloan survey, they have rigid rules about who can publish what and what procedures they have to go through. Basically, with Cosmos, I decided that we won't have such a bureaucratic nightmare, but we'll have a website where anybody who wants to do a scientific project can propose that they want to do a project, and anybody else in the collaboration can say, please add me to that. I'll help you with such and such. And that's worked out incredibly well. And also the, a lot of the people who contributed critical data sets like the X-ray imaging, Gunter Hossinger and Martin Elvis were not, original investigators on the project. They were happy to contribute their X-ray images on the cosmos field to make them available to everybody else because they knew once they became a part of Cosmos, they would be able to access, for example, the photometry from the optical, the 41 band photometry, the redshifts, which were derived, the stellar masses derived from the light on those galaxies, and star formation rates. So there's a huge amount of value added to being in a survey where the data is semi-public, and I say semi-public because when somebody contributes a data set like infrared observations of galaxies and cosmos, they have sort of, and anybody they designate, sole access to the data, for the first year or year and a half after the data has been obtained at some telescope. But then after that time, they all know that, this data will be available to other members of the Cosmos survey. And in addition, roughly, another half or year later, it becomes public. A lot of the data is released through the IRSA database. And then there's a similar database in Europe, at ESO and at Marseille.
Nick, in what ways has the Cosmos collaboration grown over the years?
Well, tremendously. Of those, say, 38 original, co-Is on the project, probably, I would say only maybe 20 are now still active using Cosmos. And that's because they've aged or they've gone out to do other, specialized projects. But as I said, we have typically, 100 people attending Cosmos meetings. So, we've ended up with a lot of new people who've contributed and who also, stimulate new research projects in it. And so, the general age of the people within Cosmos has probably shifted downwards, if anything. And, now we have two women who, another unique thing which I did was not only not to micromanage what people did, although, I listened to what they wanted to do and then suggest improvements. But after, I think it was 9 years or 10 years of being the leader of Cosmos, I said, I want to get somebody else to do this. I don't want to, be, having to write every proposal for Cosmos and, in particular, future space proposals. So I turned it over to Peter Capek, who initially had been a postdoc of mine here at Caltech, and then subsequently became a staff member at IPAC in Spitzer. And he is like a treasure trove of information. I'm usually I forget details. He remembers every detail, and I don't know how he does it, but he has a different type of mind. And he was really great. But then at some point, about 4 years ago, he decided that he wanted to go into industry. He's now working at Facebook on virtual reality stuff. He turned it over to two women, Jehan Kartopli and Caitlin Casey. First is at University of Rochester and the other University of Texas. So, we made a transition from, initially on Cosmos, I was probably 55 years old, to younger people and to women. So I'm very happy about. And Peter Capek was obviously younger. So, let me just get that phone call.
Sure thing.
Hello? Hello? Sorry.
All good. Nick, just to bring the conversation on Cosmos to the present, what are some of the key projects going on now?
Oh God, I hadn't anticipated that.
The answer is a lot, then.
Well, I mean, this project which I related on Alma is one of the more important projects. But largely speaking, even though I'm making use of data from other people and they will be co-authors on the paper, essentially most of the work has been done by me in my COVID retirement. So let's see. I don't know. Maybe I'll think about that and get back to you on. I'll try to find out what some of the more active projects are. The other thing which is happening is that people like Dave Sanders, same one who worked on the ULERs, he has now extended the cosmos concept to a field which is, branches off of the cosmos, which is 20 degrees across the sky. And that's partially because he has access to telescopes in Hawaii and also collaborators. Sure. But I'll try to find out some, one of the projects which he is doing with Meg Urey at Yale is to study AGN properties across this vast field. And to really study the, AGN, you need a very large sample, and that's the reason why they have initiated this large survey field. But, they'll never have the same quality imaging which we do in Cosmos, where, there were multiple nights devoted to a single filter on the field. But, this is a good question. So.
Clearly, though, the answer is that there's still a lot going on.
Well, part of the reason why I have difficulty answering the question is for the last 2 years, we have not had a team meeting. And the reason being, obviously, COVID.
Right.
And so that normally is team meetings, which usually last 3 or 4 days. People, even myself, are limited to like 5-minute talks where they succinctly get to the point, don't do a lot of background. And that allows us to have talks from all the young people also who wouldn't normally, in one of these other survey teams, probably get, a lot of time to be given a poster to populate. So, I think that has also served to make, the young people appreciated and more visible in the Cosmos survey. But, the lack of team meetings has meant that I and probably a lot of other people don't really know what people are doing at this point.
Yeah.
And I used to have, monthly telecons with whoever wanted to come on. And that sort of ended, I think it ended more or less after I resigned as leader of Cosmos. But they were very useful. They would largely be focused on, management issues like, how much should we stress one project versus another.
Well, Nick, now that we've brought the conversation right up to the present, for the last part of our talk, I'd like to ask a few broadly retrospective questions about your career, and then we'll end looking to the future. So first, at a very high level, if you survey all of the research you've done, all the collaborations you've been a part of, what have been some of the key contributions to the bigger questions about how the universe works, its origins, and its structure?
Uh, one of the things I pride myself on is the fact that I've spanned a large number of different areas in
Right.
astronomy and observational techniques, and then also haven't been reticent about doing some theoretical modeling. And so I love that mix of things, and I view myself as almost uniquely happy to have spread myself out rather than focusing in on one, well-defined small area. Now, at the same time, I've learned a lot from studying, say, the infrared emission from galaxies, from studying the dynamics of galaxies. When I was a graduate student, we used to map the kinematics of the Milky Way galaxy disk and, nearby galaxies. And, I've gained a lot from that knowledge. It obviously doesn't really reflect on the overall evolution of the universe, but it tells you, what is the mass of the Milky Way, how strong are the peculiar motions associated with mass concentrations in the spiral arm and clouds as they come into that area getting accelerated. And, in the case of cosmos, the main area of cosmic evolution, which I've studied, is the connection between large-scale structure and galaxy properties. But nowadays, other people have done this also. And so, one of the things I do find a little bit annoying is that, when something is done well or adequately, there tend to be people who will come in and, repeat it and put a more recent date on it. And then the thing that annoys me, though, is that young people, they usually refer to the latest paper rather than the one which basically had, the initial results. And, on the other hand, I've never really complained to anybody other than you about this, that it would be kind of in bad taste. But, that annoys me is that, and I can see myself also when I'm writing a paper, you do go to the latest review article or the latest authoritative article and then kind of work backwards from there. But, given the limited time and the large number of articles, unfortunately, a thorough understanding and appreciation of, what's been done in this area before, even in my own case, I feel that I'm deficient in that respect. But, I always certainly do try to, find the original reference and then a few of the more later references. But the thing, and I think I mentioned this to you in our first interview, the thing that also distresses me is the focus and specialization of young people. And I said that, I was particularly proud of the fact, or happy with the fact, that I didn't have to force myself, but I enjoyed going and working in new areas where I wasn't necessarily familiar. And, certainly the cosmos field is an example of that. I wasn't doing, very high redshift galaxy evolution studies before cosmos. But, you meet a whole new cast of characters, and, it's been fantastic.
Nick, on that point, I'm curious in the way that you have chosen breadth over depth in your research focus, and in contrasting that with what you might see as an over specialization of younger people in the field. To what extent is that about the way funding sources work nowadays, or how astronomy has changed culturally over the years? What do you ascribe to this trend towards over specialization?
I don't think it's a funding issue. I think it's young people when they get out of graduate school, they need to write, you know, nowadays a large number of papers, which it's obviously easier to write papers in an area in which you already have prior knowledge. But at some point, when they become a senior postdoc or an assistant professor, I would think that they would want to branch out. And, I never experienced it, but, nowadays you hear people, feeling good about the fact that they got tenure. And I actually think, tenure is kind of a bad thing because, we don't, astronomers don't need to be protected from political issues. And I think that was the main reason for tenure. And, tenure can only lead to, people eventually getting too relaxed and not, actively doing research. And I can see that not at Caltech, but at a lot of universities where, the people above age 50, 55, they end up, spending a lot of time teaching, which is good, but omitting doing any research, any significant research. I don't think it's just a matter of at Caltech, obviously, you have fantastic facilities which are available to you, but because, most facilities have public time and there also are national facilities where you can get time. But, I think it's just, laziness and perhaps lack of local stimulation for those people to, to be appreciated in their research.
Nick, in the decisions you've made to move from subfield to subfield, intellectually, what have been some of the assets of being a newcomer at a certain stage in your career and having a different perspective than somebody who might have been working in that area for decades?
I think, it's a general response is simply you come in with a more naive understanding and not dictated by, what's been done in that subfield before. And let's see, I've forgotten where I was going, but, I think, astronomy and astrophysics is not really difficult physics. And so, there's really no excuse for coming in with fresh, ideas that you want to test and then using your scientific background to fully understand, what's going on.
You're saying once you're at a certain level, there's a low bar of entry into moving into other subfields.
Yeah, the funny thing was that, starting out in radio astronomy, I always used to think that, these optical astronomers who, many of them at Caltech who I had respected, I said, oh, they do high class astronomy, precise astronomy and whatnot. And then when I started doing optical observation and working with some of these people, I found that, they were, really not all inspiring. And, they had not the same approximations, but similar approximations in what they did and similar limitations in their techniques. Radio astronomers, use computers a lot. And for modern data sets, you really need to be proficient in, computer usage or have a, young student or postdoc who's going to do the work for you. And as I said, I sort of appreciate doing everything myself as much as can be tolerated. And, I don't want to cut off support, and mentoring of students and postdocs because I really enjoyed that. But, I enjoy figuring stuff out for myself. And, it seemed to me that when I saw some of these optical astronomers and, the same goes a little bit with X-ray astronomers. That, a lot of their modeling is extremely crude, and it's what's been done before in X-ray astronomy, but it's not very integrated. I mean, in astronomy, there are two major fields of objects. One is the people studying galaxy evolution and star formation, and the other is the people who study the central black holes in galaxies, the active galactic nuclei. And, Peter Goldreich, who was one of my mentors, when I saw him, a year or two ago, he said, well, what's new in the AGN field? 30, 40 years ago, they hadn't figured out really, how the accretion happens, how the mass loss from the AGN develops, and some of the phenomena in AGN. Like these very high density emission lines, which, still nobody has really explained how they exist so close to an AGN, what they actually are. And I actually wrote a paper with a theoretician in Baltimore, but the idea was really mine, which was that these high density emission line regions in the vicinity, only a few parsecs away from the central black hole, which have a luminosity of 10 to 11, 10 to 12 solar luminosity, that they were actually photoionized atmospheres of red giant stars. So, we talked before about, my early work when I was a postdoc working with Peter Goldreich, which was trying to understand the physics of the mass loss from red giant stars. It's like, I think the paper was titled The Envelopes of something or other. You asked about it. So I could transfer some of my understanding from that earlier epoch over into trying to do these photoionized atmospheres that you might expect for red giant stars in the central star cluster around the supermassive black hole. Do they really have the properties that you would expect for that you deduce from the optical emission lines seen by optical astronomy? And it turns out that you actually do get the right parameters, just naively applying photoionization models to it. So it's not that model has been accepted, but people have moved on, and it's an example of where there's a field which everybody thinks that they understand, but nobody understands really why these high density clouds, how they can exist so close to a supermassive black hole. And in our model, which I just described, they can exist because there's a star inside the cloud which provides gravity to hold the cloud together, despite the fact that it has a lot of radiation coming from the black hole. Anyway,
Nick, is there a
that's
particular...
that's the kind of realization and idea which I find, lots of fun, and it may or may not be correct, but I don't see any real problem. But, I'm not going to sit there and keep talking about it scientifically. Better things to do.
Nick, is there a particular project that you worked on that really exemplifies the benefits of the approach you've taken over the course of your career, moving around from subfield to subfield? What sticks out in your memory in that regard?
Well, this recent project I've been doing with Alma, sort of brings everything together.
Mm-hmm.
It's built upon observations of the cosmos field with Alma and with the so-called Herschel satellite, infrared satellite, which the Europeans launched. And, I couldn't have done it without one, understanding the millimeter wave emission from galaxies, either the molecules or the dust emission. I couldn't have done it without understanding the infrared emission from rapidly star forming, molecular clouds, infrared emission, which was emitted by dust, but ultimately is a measure of the amount of stars embedded in that dust, because the luminosity was initially emitted by, ultraviolet visible wavelengths. So it kind of, this project where I'm trying to link the gas content in those galaxies observed by Alma with the infrared luminosity and hence the star formation rate as measured by the Herschel satellite, and the optical properties like the stellar mass and redshift, which is in our Cosmos survey, most of which I didn't, other people have done in modeling the photometry and deriving the photometric redshift. But at the same time, they measure the redshift to better than 1% accuracy. They also get an estimate of what the mass of stars must be in the visible galaxy.
Nick, on the technology and engineering side, what have been some of the real game changers over the years that have allowed astronomers to do things that were simply not possible previously?
Well, when I started out doing astronomy, all astronomy was done, and that was back in 1960s. Essentially, all astronomy was done with photographic plates. And my first project was measuring, the spectrum of some comets on photographic spectral plates. And God forbid that anybody should have to do that, because not only is the sensitivity not very good, but measuring these photographic plates is extremely tedious, and then also it's kind of nonlinear, so it requires very good calibration. The darkness of the photographic plate doesn't directly translate into what the intensity of light was at a given wavelength and whatnot. So that led me to certainly want to make use of computers and not do that kind of work in a dark room using a so-called photometer measuring machine. But the major optical transformation has been obviously to electronic arrays of detectors, charge-coupled devices, and the optical wavelengths. In the infrared, when I came to Caltech in the mid-'80s, one of the projects, I think it was even before when I was on sabbatical, one of the projects I wanted to do was to map the infrared emission, the near infrared emission from nearby spiral galaxies like M51. And at that point, infrared detectors at those wavelengths were just single element detectors. So I, talked to Gary Neugebauer and Keith Matthews, and I think Tom Sofer was probably involved. I talked to them about, my interest in mapping the spiral lines in M51 to see where the mass concentrations were, as opposed to just the recently formed stars that you see in the optical images. So in any case, we took their single element detector down to Palomar, and then the issue was that there was no integration between the data taking the computer, which was probably some small laptop computer, and the observing system. So we had a single element detector, which we wanted to scan across M51 to accumulate a complete image of the galaxy. And the technique to get positional information of the different scans out, which Gary Nogebar suggested, which was really quite nice, was that the detector, which was being plotted on the strip chart, would pull the plug on the detector and put it back in again at the end of every scan line. So you could tell when a scan ended and began. And then, we knew how far we were stepping between lines. But anyway, so that was kind of fun to do that kind of hands-on approach. Obviously now, the pointing system from the telescope is integrated in with whatever data-taking computers they have. But, that was back in, 1980, which, was long after people started first doing infrared observations. And on the other hand, data reduction software keeps improving and getting more complicated. And so at some point, if I had some optical data at this point, I wouldn't want to reduce it myself. I would, get some younger person to do it. Just because I have no urge to try to understand how to operate this software.
Sure.
I much prefer to do some analysis, which is on a small scale, but which is maybe more physically interesting.
Nick, on the institutional side, to go back to something very interesting that you said in our previous discussion, when you had that conversation with your colleagues and you talked about the complainers and you exhorted everybody to remember that Caltech has one of, if not the best astronomy program in the country, perhaps even the world. You also said that it's not that the people are so much better at other top flight institutions. So that prompts me to ask, if not the people...
No, well, I'm not sure what you misspoke. It's that I didn't think that necessarily the people at Caltech were that much better.
That's exactly right, that the people are not that much better. So that does beg the question, if
I don't think I said that to the faculty that I was addressing.
No, but to me, right, exactly. To me, you said that. It does beg the question, though, that if it's not the people, what is it? What has been Caltech's secret for the excellence that it has demonstrated in astronomy over the years?
Extremely good students, the best crop of students who, Caltech has a good reputation in astronomy, an excellent reputation. And so it does attract, first choice.
Oh, you're touching the microphone again. I couldn't hear you. There you go.
It does attract sort of the top tier of incoming graduate students each year. And that's becoming less so. But the thing which Caltech really has is guaranteed access to, several unique facilities. And certainly, the Keck telescope is a major advantage that Caltech professors have. And then, having your own radio telescope, radio observatory. But Caltech was not unique in this because, Berkeley had a similar observatory, and Illinois used to have a radio observatory. But, the Caltech Radio Observatory has actually survived up to the present and is going strong now. Although it turns out today, if you may know, there's a big brush fire, which is headed, surrounding the observatory. But at some point, you'll interview Greg Hallinan, who's, a really great character to get to talk. He's not close to retirement, though. you may have to stay at Caltech for a while.
I hope I do. Well, Nick,
But the other thing is, of course, at Caltech there's a fantastic mix of disciplines, and so I could work with physicists, like the infrared group. Uh, I haven't made use of a lot of intellectual discussion with things like aeronautics and whatnot, but I certainly used to see them at the Athenaeum and enjoyed that kind of interaction. But the and I don't mean to imply that the Caltech professors are not good. They are good. It's just that I think they maybe have a little bit too easy life, and they aren't pushed enough. In the case of being a radio astronomer like myself, we always had to go out and get funding from National Science Foundation to support the Owens Valley radio telescopes. Whereas in the case of Palomar and even Keck, they're really, nowadays for instruments, they do go to the NSF to fund new instruments, but the bulk of the support for Keck is provided by, I think, the Keck Foundation and by Caltech and UC out of their operating budget. So, for some reason, the radio astronomers have always been in the habit of having to raise their own funds. And that's to some extent true of the infrared astronomers in terms of salary support. But not in terms, they've obviously made use of Palomar. Okay.
Well, Nick, one last question looking to the future. Obviously, your career demonstrates right now Emeritus does not mean retired. For however long you want to remain active in the field, what's most important to you? What do you still want to accomplish?
That's a slightly delicate question, but because I actually, I do sculptural welding as a hobby, and I've put that off for many years, just doing, say, one project every couple of years. And I really want to get back to doing that if I still have the physical energy to do it. So this Alma project, which I've described, I think that may be my last big project. I hope it's my last big project because, I'm now 77 and I really want to be able to do some, another thing, which would be artistic. And I've found in the limited art, which I've done, which is all welding type art, in the limited art that I've done, I found a great deal of intellectual joy from discovering, starting from, raw metal where you don't really know what you're going to do, and then discovering that the final result actually people like and are interested in. So one of these days I'll show you some pictures.
What's going to become of Alma? What do you hope to do for as long as you'll be a collaborator on it?
On what?
On Alma.
I'm really somebody who makes use of the data in their archive. So I'm not actively a collaborator, although certainly I'm a senior person in the field. And so, the work that I did and what Shanila did is initiated the impetus for Alma. But I don't think either one of us is really active in helping Alma at this point. So, anyway.
Do you see your artistic sensibilities as an outgrowth of your career in astronomy, or do you tend to think of them as separate endeavors?
I tend to think of them as separate. I don't do astronomically oriented for sure.
Well, I'd love to see him sometime.
We do some furniture and then also a mobile of fish with screens on both sides of the fish for the two sides of the fish.
Wonderful.
Get moire patterns as the thing rotates. But the strong winds, which we have, actually bent the tail. So I need to, reconstruct the tail a little bit. And, because I had the Alma project, which it's easy to go sit at a computer and stay clean. I didn't want to go out into the grimy shop and get oily and dirty. So, a little bit of laziness. And, I also needed to finish the Alma thing for, I give this Russell Prize lecture, and that'll be the main focus of what I talk about there.
Always something to look forward to. Well, Nick,
That's in Pasadena, by the way. So in mid-June, so you should probably come to that.
I would love to. Well, Nick, this has been a fantastic set of discussions. I'm so glad we were able to do this and capture all of your research and contributions. I'd like to thank you so much.
Yeah, and